So today we're going to talk about electric circuits, specifically how current and Ohm's law work together in electric circuits, and some of the basic components of circuits that we'll be seeing. So the first thing we need to know about is current, which we represent with an I in all of our equations. Current is the rate at which charge, which is Q, flows past a point on a circuit. And remember, rate is one of those words that we can use to think about our equations. Anytime we see the word rate, it means we're changing something every second. In this case, we're changing the amount of current or the amount of charge every second. It's how much charge is flowing past a specific point every second. So in our equation, we have Q for charge divided by T for the amount of time. So in our equation, you can see current is Q divided by T, and we know current, or not current, charge, it has a unit of coulombs, which is capital C, and time has a unit of seconds. So current, the unit for current is actually 1 coulomb per second, but we have a special word for that because we use it so often. It's called an ampere, named after a scientist. Anytime you see a capitalized unit, like capital A, there was a scientist who was very prominent in this field of study. We can think of current in a circuit the same way we think about current in a river. It's how much it is flowing through the circuit. And this little bit of information here is very important, but we're not going to talk about it very much in this video. But in order for charge to flow, in order for there to be a current, you have to have some sort of battery. Batteries provide an electric potential difference. If we're thinking about the rivers again, batteries provide some sort of difference between one point and another point, kind of like for a waterfall in a river or any elevation difference in a river. In order for a river to move anywhere, there has to be a difference in the height. And batteries provide a difference in the electric potential. So if you want to think of the battery is lifting up these electrons. They're kind of giving them a certain amount of potential energy, electric potential energy, so that they can flow through the circuit. You also need the circuit to be closed. So that means from one end of the battery, you should be able to trace along a wire through any components in the circuit, and then all the way back to the battery. If there is any break in that circuit, then none of your circuit will work. And last but not least, you have to have a device that draws current. So you have to have a resistor, a light bulb, a motor, anything that will use the electricity in that circuit. I want to go back to this closed conducting circuit for a bit, because sometimes it's a little hard to see. And one thing you always need is a way for the electrons to go into your circuit and a way for them to come out. So in this picture below, we can see that maybe the electrons go this way through the light bulb and then back to the battery. They have one way to come out and one way to go in. One way to go in, one way to go out. They must have separate doors like that. But if we're thinking about charging, say, a smartphone, so say this is a smartphone, we've got the one wire and then it goes into the wall. How is that wire providing two paths, right? We need an in and an out, but it looks like there's only one wire connecting it. And think about if we have a battery and a wire and a single light bulb. This light bulb that I drew will not turn on connected to this battery, but if I plug in the iPhone to the wall with the one wire, then the iPhone will charge. Why is it that the iPhone will charge when it's connected with one wire, but the light bulb will not light up? And the reason that is in this one single wire, there's actually two wires. And you can see that, you have a little hint when you have your cube. So you have the USB converter to plug in, right? The USB port goes here, and this part goes into the wall. There's actually two prongs, one for the current to come in and one for the current to come out. And in the wire, especially if you have an Apple wire, sometimes the Apple wires get a little frayed and they start getting holes in them, you should be able to see that there are actually two sets of wires in there. So even though it looks like just one wire, we're still completing our circuit and having it come all the way back around. Now, way back when electricity was first being experimented with and first being discovered to any good degree of certainty, way back in the 1800s, electrons were new on the scene, and nobody really knew too much about electrons. So everybody presumed that current would be the direction that a positive charge would move. So everything would move from positive to negative. Electrons are not a positive charge. They are a negative charge. So what's actually happening is electrons flow the other way, the opposite way, in a wire from the current. We still use current as positive. It doesn't change all that much in the numbers. So it's just a little interesting thing to keep in mind. Drift speed is the average distance traveled by a charge carrier, which is an electron, per unit of time. We like to think that electrons zip through the wires with no trouble at all, and for the most part they do. But for every second that an electron travels, it only moves 3 or 4 centimeters. It doesn't move very far. So how is it that when we turn on our switch, we instantaneously, or nearly instantaneously, have light? If electrons are moving so slowly through the wire, like 3 or 4 centimeters per second, why is it that we can instantaneously get light when we turn on the switch? So the reason we can turn on the switch and get light is because where do the electrons come from? Do they come from the switch and have to come all the way around from the switch to the light? Do they come from the battery or generator? and have to come all the way from the battery? Where are they coming from? They're in the wire itself. So when we have a wire and all these electrons, the minute we turn on the circuit, it starts a chain reaction through the whole wire. All of the electrons start moving. So even though we have electrons at one end of the wire, or even though we have electrons by the switch, they don't need to be the ones that travel to the light in order for us to get light. The only thing that needs to start moving are the ones that are already in the wire, and there's electrons all throughout the wire. And then also, high current is caused by many electrons moving at once. So we don't have single electrons traveling all the way from the switch to the wire we have, or the switch to the light bulb. We have thousands and thousands and millions of electrons traveling through our circuits. And some other things I want to talk about are alternating current versus direct current, or AC/DC. Alternating current is a current that is changing directions. So 1 minute the electrons are flowing away from the switch, and then the next minute they're flowing back towards the switch. So they're constantly going back and forth and back and forth and back and forth. And you can kind of think of it like waves on a beach. First the waves come in, and then the waves go out, the waves go in, the waves go out. This kind of current is what we get from our wall outlets. Any power source that we have is alternating current. And sure enough, that's also what was used in electric chairs. And we'll talk about why they used alternating current in just a couple minutes. Direct current is current that just flows one way continuously. So instead of being like waves on a beach, it's more like water through a hose. The water in the hose is not going in and out and in and out. It's only going one direction. Any sort of battery, like a AA battery, AAA battery, D battery, those are all going to be direct current. Also, defibrillators are direct current. They have the two charged paddles, and they're going to, the charge builds up on the paddles, and by charge I mean the electrons. And then when they discharge the paddles, all the electrons go from one paddle to the other. So that is a direct current. So going back to why electric chairs use AC current and defibrillators use direct current, AC current, because it's always going back and forth and back and forth, when your heart, which needs electrical pulses to beat, when your heart encounters an AC current, it starts spasming because of that back and forth and back and forth. When it encounters a direct current, it contracts, but then once that current is gone, it can start beating again, right? So somebody who has had a heart attack and whose heart is out of rhythm, a defibrillator is a good thing because it clenches the heart all at once, and then when the heart releases, it can go back into a rhythm. An AC current, which is the back and forth, can send the heart into a heart attack because it's just sitting there spasming. And not only is blood not circulating, but it's getting out of sync, which is bad news. Now, For anybody listening, I am a physics teacher, which means biology is usually not my strong suit. So if I misspoke on any of these things, please let me know, and I will try to correct it in the next video. But to the best of my knowledge, I think I'm okay for the most part. So, electric potential difference. We mentioned it before a few slides back. It allows the current to flow so that, because it's got that difference. So like water in the pipe. You can see in the image. Water won't flow if it's on a flat surface. There has to be some sort of difference in the elevation. Electric potential difference has a couple different names. Sometimes it's just called electric potential, and it's also measured in volts, so it's often called voltage. And again, volts is a capital V, so that's a hint that these units were named after a scientist. Charge is going to move from high potential to low potential, but again, this is by charge we mean the positive charge. It's going to go from high potential, which is going to be positive, and move towards low potential, which is just like what a positive charge would do. If we put a positive charge near a positive charge, it's going to be repelled by the positive charge and attracted to the negative. Ohm's law relates voltage or electric potential to current and resistance in this way. So voltage equals current times resistance. And we can rearrange that equation so that we could solve for current or resistance. Something else to keep in mind is that voltage is electric energy divided by charge, so it's how much electric energy each charge has. Depending on your class, you may use that more or less often. And then in this chart down below, we have the symbols, which we would see in our equations. So voltage is a V, and the unit for voltage is volts. This is one of the few nice ones where the symbol is the same as the unit. Current is represented by an I, and the unit is amps or amperes. Resistance is an R, and the unit is ohms, which is a capital Omega. And the last thing we can talk about is electrical power. So remember, power is the rate at which energy is used or transformed or transferred or supplied. So every second, how much energy are we using? So power is the energy divided by the amount of time. The unit is still the same. It's a watt, which is capital W. And if you've ever had a chance to look at your parents' electrical bill, you'll notice that the electrical bill charges you for kilowatt hours. So if we have a watt or a kilowatt, which is 1,000 watts, times an amount of time, so we're taking a power times a time, watts times hours, kilowatts times hours, that's actually a unit of energy. Now back to the left side of this slide, we have power is going to be the amount of current we have times the amount of voltage. And these equations come from the fact that we have current, which is charge per time, and we know that voltage is energy per charge. So if we have current times voltage, I times V, the charge will cancel and we'll get the amount of energy divided by time, which is our equation for power. So power is current times voltage, but we can substitute Ohm's law for V, which would also get us power equals the current squared times resistance. Or substitute I equals V divided by R, which would get us power equals voltage squared divided by the resistance. So depending on what information you are given in your problem, you could use any of these equations to solve for power. So our next video is going to be about simple circuits, which are just series circuits and parallel circuits, how we draw them, what their properties are, and how we can solve for different things in those circuits.